Good evening, and welcome to North Penn High School. How is everybody this evening? Super, it's so great to see all of you. I'm really excited to share with you some exciting endeavors that we've been taking here at North Penn, and share with you the 31 students that are going to be up here on stage from the Engineering Design Development course, as well as some students from our North Penn NASA research team, and then you'll also see some students from our Engineering Projects and Community Service Club as well this evening. So there's a lot of exciting things. Now, for I know many of you are familiar with the Engineering Academy and our program here, but I know we have a lot of visitors who may not. So I'm only going to take a few minutes, and you have to push me along, say, come on, Mike, let's go. But I want to give you a little bit of background so you understand a little bit about our program and what our students have gone through here and how they're going to be so much more prepared once they graduate in how many days?
7.
Yeah. Yeah, I am so excited for these guys because they're ready to take on the world. So you can actually see the team names that are up here, and the team names represent each group. They decided to, and I asked them to come up with a name that's representative of the research that they're doing. So you'll see that tonight as they begin. The Futures Near program stands for Nanotechnology, Education, and Research, and it's something that is unique to North Penn. There's nobody else in the world that runs this. This is something that started here back in 2003, and I'll talk a little bit about that as we go through. The Engineering Academy itself is within our Technology Engineering Education Department. And the Engineering Academy was started in 1999 with a purpose of giving our students the opportunity to learn about engineering. We graduate over 3,000 students from here. Several hundred go on to engineering, and back before '99, we were saying to each other, wait a minute, nobody's coming through our department. We need to figure out why. And so we decided to open up and start something called an Engineering Academy. And to do so, we connected with a program called Project Lead the Way, which is an international program that is designed to introduce engineering to students. It's really exciting, and these students will tell you a little bit more about it. So the Engineering Academy is within our Tech Ed department, and then we also have 4 or 5 different clubs that we run after school to give these students more opportunities to do things above and beyond the curriculum that you'll hear a little bit about more this evening. Our 5 course sequence is on the right, and the students you're going to see this evening presenting on stage are part of our capstone research course, also known as EDD, or Engineering Design and Development. EDD is our senior capstone course. The students go through the 5 course sequence. When they get to this point, they're going to take a look at, wow, can I apply what I've learned in the past 4 courses that got me to this point of where I am? And if you take a look, and if you're familiar with the National Academies of Engineering, they actually have listed 14 grand challenges for engineers to take a look at and to tackle globally. Every one of these research teams tonight that you see are actually aligned with that. Not purposefully, they just realized if we want to change the world, if we want to make the world a better place, how do we do that? Let's take a look at problems that are out there and then develop solutions for them. So you'll see them this evening do that. They'll go through the 6-step engineering design process, defining the problem. What is the problem? Does it really exist? They have to justify it. Is it really needed to be solved? And then who's done it before? What's the current state of the art, and how do we make it better? So you'll see these students talk about that a little bit and then jump right into what did they do this year to make the world a better place in solving their problem. And they are in step 6 this evening, present your work. Because there's 2 things that engineers need to do. Number 1, document it. If you didn't document it, you didn't do it. And number 2, if you didn't share it with the world, who's going to know about it? So it's important that they learn these skills now, because pretty soon they're going to be out working in university level or out in the work world, and they have to share their work. And so this gives them a little bit more of an opportunity to do so. I have a little quote here. Scientists discover the world that is, engineers create the world that has never been. It's kind of neat when you think about that, because wow, we take science, it's very important, but we use it to the best of our abilities, and we learn about new things, and these students will tell you about that this evening. So there's also a nanotechnology component here, again, unique to North Penn. The nanotechnology research started in 2003 when I signed up for a research program at Drexel University. I signed up to do something in electrical because at the time I was teaching digital electronics in our engineering academy, not EDD. And when I got an email, Dr. Coe sent me this and said, here, Mike, this is your first project. And what I'm doing right now is what I did when I saw this. If you can see, the electrostatic fabrication of ultrafine conducting fibers, polyaniline, polyethylene oxide blend, I was like this. And then when I read through the abstract, it was even worse. And I'm like, honey, to my wife, I'm like, honey, I don't know. She's like, well, how would your students feel? I'm like, okay, you're right. I will definitely make sure that I try this. And well, needless to say, in 2003, I was scared to death. And it's changed my life. And in turn, hopefully changing the lives of your children and these students here. So I'm really excited. While I was in the summer program, I learned more about material science. We learned about how we can take forces that are around us. You know, we think of mechanical forces, pressures, we push on things. But did you know that light is a force and heat is a force? And wow, if we could take heat and light and have them do crazy things, we could revolutionize the world. So getting the students to think about that now while they're 17 and 18, not when they're in their graduate or PhD research at 25, 26. Get them thinking about that now. So we learned about material science, and then we studied nanotechnology. Without getting into nanotechnology, other than we're talking about things that are a billionth of a meter. Can you imagine a billionth of something? You know, you cut it in half, all right, there's 2. You cut it in half again, there's 4, and you keep going. Well, imagine a billionth of something. It's so small that 1 billionth of a meter, the human eye can't see. So we can't use traditional optical microscopes to analyze it. So we study nanotechnology, and these students work at the nanoscale. They work with materials that are smaller than the wavelength of light. It's absolutely amazing. And not every team is doing nano. This is not a nano course, but there is a nanotechnology component that I think is so important because it's revolutionizing medicine, healthcare, industries, that I really feel like they should know about it. And so we cover a lot of that in class. We actually prepare polymer nanofibers. We make fabric at the nanoscale. And you can take a look here. We have a high voltage DC power source, 0 to 30 kilovolts. It's 30,000 volts. Applied to a liquid polymer solution, and it causes a polymer jet to come out. Without getting into details, you can use this for water filters, air filters, sensors, energy harvesting nanofibers. You'll hear about some teams that are looking at how can we actually generate electricity from rain. Yeah, isn't that crazy? It's pretty exciting. Advanced drug delivery and so much more. And here, if we can't see at the nanoscale, what do? We use a scanning electron microscope. There's an SEM in the gym you're going to see this evening. It's awesome. That's all I can say. I am in awe every time I work on this high advanced piece of equipment. The students will tell you all about it as well, and you can actually see them here working with it. We've had it in the lab several times this year. It's really exciting. And we couldn't do all this without support from many companies. I've written for grants. When I found out about, I want to teach nanotechnology and I want to teach research, how am I going to do this? And there's no money. I can't just pull money out of the budget. We don't have a budget for this. I wrote for grants, and all of these companies gave us a boatload of money. I mean, I'm humbled. $65,000 we've collected since 2005 to run this program. And it's amazing. And our own North Penn Educational Foundation, if you're not familiar with them, give these students money every single year to help them with their research endeavors. We couldn't do it without them. So we're really excited. So in 2005, when I first started teaching electrospinning, what is a nanofiber? How does it work? Now, you can take a look up here at all the different things. How do we harvest energy from the rain, wind, and heat? How do we make batteries more efficient? How can we get electricity to developing nations? How can virtual reality improve education? And we can go on and on and on with all of these different things, and the students tonight are going to tell you about it, and I'm so excited for that opportunity. So what's next? Well, this year we're working with NASA, and part of, we have a North Penn NASA research team, which you're going to see speak tonight. I'll come back out and tell you a little bit about it then, after them, as well as the Engineering Projects and Community Service Club that I run here after school as well. What's next year going to bring? You never know. It's absolutely amazing though when your point of view and your focus opens wide, and you start looking at the problems around us and how can we change the world. So it's really exciting. So, with that being said, what I'd like to do is hand it off to our first team, which is ARD Industries, and they're going to talk to you about photovoltaic, piezoelectric, and thermoelectric energy harvesting. Thank you very much.
I'm Alex.
I'm Bo. And I'm Darren, and we are ARD Industries.
This here is a picture of our PVDF nanofibers. It is a 9% solution containing acetone and DMSO. This is just a sneak peek of what we have to offer. So, what if we can harvest energy from which Earth can freely provide us? What if we can harvest energy from somewhere else other than the inefficiencies of today?
Well, as of today, we provide ourselves with energy in numerous ways. The problem with the current methods is that they generate electricity using the resources of the Earth and can possibly be dangerous. Our proposed solution is to create a device that uses a nanogenerator. This nanogenerator will be able to create voltage and harvest energy. It'll create voltage by using the light of the sun, pressure from rain, and changes in temperature.
When we first set out to find a way to complete this task, we decided upon doing it one aspect at a time, starting with the pressure from rain, then moving into one of the other two once we completed work on the first one. We then proceeded to break apart a research paper that we had and discovered that some of the materials we couldn't actually get on time to complete all of our work needed. So we came up with a backup plan and we made two different solutions, one being 9% PVDF and the acetone DMSO mixture, and the other being the 18% PVDF with the acetone DMSO mixture. We then proceeded to do a few electrospinnings and discovered that we were having trouble removing the fibers from the aluminum that we were spinning to. So after that, we had a new task and we found out that you can easily spin to wax paper and it saves you the struggle of getting the fibers off of the aluminum foil in the end. And then we proceeded to cut aluminum tabs because you cannot get an electrical charge to flow freely through the fibers and wax paper alone. So we cut 2 aluminum tabs and put them in contact with the fibers, and to seal them, to protect them from any external forces, we ran them through a laminator, which also helped increasing the conductivity. We then proceeded to measure our 4 tabs we made 4 tabs and measured it in 2 different ways. The top being our lateral, or going across the surface of the fibers, and then the bottom 2 being our transverse, or going through the fibers, which we then folded the fibers in half to make that a little bit more easily for us. And then here you can see all 4 of our tabs up against each other, and through this we found out that measuring our 9% and 18% transverse going through actually produces the greatest output voltage compared to measuring just across.
What is next? What's next is that we would like to we hope to enhance our PVDF nanofibers with the use of multi-walled carbon nanotubes. By doing this, we can multiply the amount of voltage produced through the piezoelectric effect of one single tap. We also hope to utilize different other aspects of our environment, including thermal and solar energy. By doing this, we hope to create a device that can harvest all aspects of our environment. Thank you, and we hope to see you next week.
Hi, I'm Brian Mowat.
I'm Julie Santos.
I'm Harris Levine, and we are EVERT.
These are pictures of a classroom about 100 years ago. As you can see, the quality of the pictures isn't so good. These are pictures of now. The classrooms, what they'd look like if you walked into the North Penn High School right now. The quality of the pictures, 10 times better. Now, how come the technology used to take these pictures isn't depicted in the photos themselves? Well, that's a problem. Technology is advancing at such a rapid pace that education can't keep up. And that's a huge problem, because with technology in the educational system, we'd be able to give students a more hands-on and personalized learning experience.
With that, we took a look at some educational philosophies which lent themselves to our research. We have experiential learning, which is defined as learning from reflection on doing. And so students can forge their own paths, succeed and fail for themselves, which brings us to personalized learning or student-centric learning. And this would address the diversity of individual learning needs and preferences so that you can be an active participant in your own education. So virtual reality is a three-dimensional computer-generated environment in which the user can interact with and explore in. And there's two types of virtual reality. There's mobile virtual reality, which can work off your smartphone. And then there's desktop virtual reality, which can work off the processing power of a computer to generate more realistic-looking environments. So currently, virtual reality is used by the United States military in order to train soldiers for combat scenarios. It's also used in distinguished universities like Yale or Stanford. Virtual reality is proven to improve operating room performance. And also there's a huge virtual reality gaming industry which exists.
So how are we using virtual reality? We hope that by introducing virtual reality into the classroom, we can personalize the experience to each student individually. That way they can learn hands-on at their own pace without the distractions of other students.
So our first lesson, we worked with a teacher, Mrs. Kelly, and her emergency care class. Her wounds unit was what we focused on. In Unreal Engine 4, we designed an immersive environment where students were able to see what different wounds looked like, such as abrasions, avulsions, and puncture wounds. And we also were able to teach them how to treat the wounds in real time.
Another experiment that we ran was with an English class, Mrs. Felder's class. They were reading The Catcher in the Rye, and we took the students on a virtual tour of New York City so that they could better see the setting of the book.
We found that students were eager to embrace new technology in the classroom. Also, when using the virtual reality, there was little to no external distraction in the classroom. And many students felt that virtual reality was beneficial in understanding the content of The Catcher in the Rye by J.D. Salinger.
So what's next? What we hope will happen is that the people who come after us will create more environments and gather more data so that we can further prove that virtual reality does have a place in education to further the educational experience as a whole.
Thank you for your time, and we hope to answer all questions.
My name's Nate Chrysler. I'm here with my partners James Drinkwater and Jake Yoder, and tonight we'll be representing the team Innovo. Mobile electronics die. This is a fact that everybody knows. These are a couple of today's devices that are used every day worldwide. You have your cell phones, you have your laptops, you have your portable gaming devices, but you also have your mobile electronics like your cars and your airplanes. However, all these things have two things in common. One, they are all dependent on batteries, and two, they're used every day worldwide. These devices have become so prevalent within today's society that taking these things away would disrupt many people's daily rituals. However, when the batteries within these devices die, that takes these devices away from us. Our research attempts to look into this problem and find a solution.
Here we have three of the most popular batteries: lithium-ion, nickel-cadmium, and lead-acid, which is in your mobile transportation. Here we have a lithium-ion battery with the anode and cathode on either side, the electrolyte in the middle with the separator separating them both. Now the separator allows the battery to not short circuit nor surge in power. Here we have the two most popular uses for separators. We have polyethylene, which is used in your everyday water bottle, and polypropylene, which is used in ropes. Now the problem with both of these is that they deteriorate very fast, which is why your phone never gets the same amount of charge when you charge it a second and third time.
Polycaprolactone was one of the most popular solvents that we used within our separators. There were many possible candidates that we used within our separators. However, this one gave us some of the best wettability and some of the best conductivity for our separators.
So what we do with the PCL is we combine that in a solution with acetone. So it's a 20% PCL solution. We put that into a syringe and we electrospin it. So we hook that up to a pump and it extrudes at about 1 milliliter per hour. We apply a high voltage to the positive to the needle of the syringe and they ground about 10 centimeters away. This difference in voltage pulls the solution out into this Taylor cone that you see here. And when it's at the nanoscale here, the solvent evaporates. So in order to make sure that we're spinning correctly and that we have a good spin, we take a glass slide and we get a sample of the spin while it's going right at the beginning before we finish our 50-minute spin. So as you can see on the side, this is an example of a good spin where it's very uniform, there's no globs or breaks in the fibers. So what we wanted to do is we wanted to see how it looked after our 50-minute spin. So we spun directly to a glass slide on the collector plate for 50 minutes, and we looked at how dense it was. We compared that to a stock separator that we used later on in testing, and as you can see, they're very similar. They're both very dense, but the one that we spun, the center, is a little bit more dense than the outside. You can see that the porosity, the space in between the nanofibers, is different. So to combat this, we decided to align the nanofibers. By doing this, we believe that it would increase the consistency of the porosity. So in order to spin these aligned fibers, we created this design with a motor and a goalpost. The goalpost rotated, and that became our ground plate, so we spun directly to it and it aligned the nanofibers.
Right here we have our testing battery. Now we have the cathode on the bottom, our electrolyte, and it was just salt water and a separator, and the magnesium on the top. Here we have our testing apparatus, which we took, we measured voltage and amps over time.
So as you can see here, the blue line, which is our random fibers, that's the one at the bottom. It drops off halfway through. That's from some tests that did not complete all the way. We believe that's from the inconsistent porosity. The one in the middle, the yellow line, that's our stock separator that we tested. That was fairly consistent throughout, but as you can see, the red line at the top of the 9 nanofibers was a little bit higher, and it was also very consistent. So that proved our hypothesis correct, that the aligned nanofibers and the increased consistency of porosity did help with the battery.
If we had more time for our research, we would look into finding the most optimal angle of alignment, because as of right now, we're not sure if 90 degrees is the perfect angle of alignment or if 80 degrees is the perfect angle of alignment. And if we are able to find that perfect angle of alignment, that can give us the best uniform porosity throughout the separator, and a better separator means a better battery. We would also like to find a better polymer mixture, because while we do believe that PCL and acetone work very well together, there may be better solutions out there that can give us better batteries. We are also looking for a better testing apparatus, because throughout our experiments, while it did give us very good results that we were looking for, many times while we were testing, there were a lot of uncontrolled variables that we couldn't really control, and so we would look to eliminate that with a better testing apparatus. The last thing we would look for, if we had more time, is increasing the discovering the longevity of the separators we produce. Because throughout our testing, we looked at how well these separators work through about 20 minutes. However, we're not exactly sure how long these separators work. And so if we had more time, we would like to explore all of these things. That concludes our presentation. I want to thank everybody for coming out tonight.
Hello everybody, I'm Brian Pilot.
I'm Matt Shaw.
I'm Tyler Euler. And we are MagTech. 1.3 billion. That is the number of people on this planet that do not have access to electricity. Imagine waking up one morning and thinking, wow, I don't have access to my phone, or hot water, or even lights. But then think, this can all be solved with just salt water and 2 common metals.
So current solutions for providing electricity to the public tend to be very inefficient and they produce pollution for our environment. These solutions include the use of fossil fuels, nuclear, solar, and wind energy. So our goal was to create a efficient and environmentally friendly source of electricity that the whole world would have access to.
A metal air battery works off of a simple chemical reaction between the metal and the oxygen in the air. The reason the metal doesn't react normally is because there's nothing for the electrons to pass through. It needs an electrolyte such as salt water. In our fuel cell, we have magnesium as our metal anode, we have a iron disulfide as our cathode, and then we have a separator that holds the electrolyte. This year we electrospun 2 polymer nanofibers, PVDF and PCL. We also embedded both with copper nanoparticles to try and increase the conductivity of them.
This is a graph of all of our average power outputs of all of our fuel cell tests. This includes tests with used materials, regular stock materials, and nanofiber-based materials. And as you can see from the graph, everything is all like jumbled up and we got very inconclusive data from all of our tests.
Everyone knows what a AA battery is, and that's why we chose to compare it to our fuel cell. A AA battery creates 1.5 volts and about 200 milliamps of current. Our fuel cell created the same 1.5 volts, but only created about 15 milliamps of current.
So, if we could further our research, we would have liked to look into different nanomaterials for use in our cell. But one other thing we also would have liked to do was look into different electrolytes to use instead of just basic salt water. So, thank you everybody for coming out, and we hope to see you in York's gym.
Hello, my name is Zanny Grant.
I'm Justin Rosowski.
I'm Evan Corrades. And I'm Sam Rooney. And together we make the nanopolymer systems. Now, I know many of you here have sometime gotten injured and had to get stitches in your body, and know the agony throughout the weeks of the healing process, where slight contact will suddenly a jolt of pain throughout your body. If only there was some way that we could shorten this period and make it more comfortable. Well, we at Nanopolymer Systems bring that to you, and we bring shape memory polymers.
And what is a shape memory polymer? Well, it's a polymer that displays a shape memory effect. And what that means is that if the polymer gets deformed, you can apply a stimulus to it so it reverts back to the original shape. Now, stimulus is some sort of change that's in the environment. It can be heat, it can be light, it can be electricity, it can be a chemical change. There are also lots of different types of shape memory polymers out there. Some are more elastic than others, and some are more strong than others, but all of them have great promise.
Now, there are many current solutions in our world today that could use a little bit of touching up by shape memory polymers. Such things are drug-eluting stents and bare metal stents. Now, these are used for something called percutaneous coronary intervention. What this is simply the clearing of a blood clot in your arteries. Now, the problem with these is after weeks in your body, a clot could reform, or your artery wall could reform as well and close your vein, causing certain cardiac death. There are also stitches. Like I said before, they're very uncomfortable and last a long time. Similar to stitches, they're cast. Having them carry them around, being heavy and also robust, it's really annoying to have them around for at least months on end.
So on the subject of cardiovascular stents and stitches, the cardiovascular stents and stitches, when they're introduced into your body, they have biodegradability, and because of this biodegradability, they will break down inside of your system, and this will remove the need for surgery. Also, the stents and the stitches will be, oh my god, the stents and the stitches, because of that, they have response to stimulus. And because of that response to your stimulus of your body heat, with that, we've also found a mechanical application in the aeronautical field.
So these are materials we use to make our own shape memory polymer. We wouldn't make our own so we can understand how they work and learn more about it. And our shape memory polymer was mainly polyethylene glycol based.
Our procedure for making a shape memory polymer begins with first we UV cure our polymer solution to solidify it to actual working polymer. After which we apply heat to that polymer to make sure that it maintains that polymer state. Then we remove the polymer from the apparatus that's holding it and rinse it off to have a functioning polymer at use.
So we performed multiple experiments throughout the year. I'd like to highlight two predominant experiments that we did this year. The first experiment we did involved a glass slide, and on that glass slide we had a film form. Now, this film wasn't as successful as we would like it to be, but it was a step in the correct direction, and it would eventually lead to our second experiment, which we had a physical polymer form on it, and this polymer formed on a piece of tin foil. This polymer then led to further research. This further research was what we needed in order to get the final result. So this polymer I was just telling you about, there was an experiment we did with cold and hot water, and we put that into cold and hot water, the polymer, which you will see now.
Alright, in this experiment you see how a shape memory polymer works. That polymer is folded in half and placed in the cold water. That water is supposed to solidify the polymer so that it maintains that folded shape even after removed from cold water. And if you're wondering, the wires are supposed to indicate the temperature for the cold and warm waters for recording purposes. Now the polymer is placed onto aluminum foil for observation, and it maintains its folded form, proving that that concept actually works. Now we actually place the polymer into warm water to see if the shape memory effect part actually works along with it. And it is a success. And now it is now unfolded and turned into its original shape, proving that we did it right.
Now, in the future, if we were to have more time, we continue creating more apparatuses and larger materials. With these larger materials, we see to have more accurate tests. These accurate tests will allow us to have a leap forward into the application area. We see to apply ourselves into the biomedical field by creating stents and stitches as we mentioned before.
Thank you for your time. We are in the polymer systems. If you have any questions, please talk to us in the auxiliary gym. Thank you for your time.
Newton's first law of thermodynamics states that energy can neither be created nor destroyed. Rather, it's transformed into other forms of energy.
I'm TJ Schmidt.
I'm Jason Elstrom.
I'm Anthony Brigidi, and we are NET. And the goal of our research this year was to create ways to harvest natural energy from the environment through sunlight, weather, and temperature differences.
So the first type of energy harvesting material is photovoltaic. These materials can generate electricity from sunlight, or more specifically, ultraviolet radiation. The most common form of photovoltaic material is the silicon solar cell, which is used in solar panels. However, silicon solar cells are very expensive and difficult to produce, but there are alternatives. Our research led us to the dye-sensitized solar cell, or DSSC. These cells are much easier to produce and just as efficient, if not more, than the silicon solar cells. These cells are made of indium tin oxide coated glass slides which can conduct electricity, an iodide electrolyte solution, berry dye, titanium oxide nanopowder, and a carbon layer. As you can see by these graphs, our dye-sensitized solar cell performed as well, if not better, than a manufactured silicon solar cell.
Now, the second form of energy harvesting was through piezoelectricity, which is defined as any crystalline structure that, when force is applied to it, it creates an equal and opposite charge to the direction of the force. Now, the way that we started our research was we bought a piezoelectric tab online, and this piezoelectric tab uses polyvinylidene fluoride, otherwise known as PVDF, and PVDF is a piezoelectric polymer or plastic. Now, we tried replicating this by using research-grade silver paint, painting a layer of that on two sides of a piece of lamination, and electrospinning PVDF nanofibers to one of the sides. After we had our collection, we folded the lamination on top of the other silver, laminated it, and we had our tab. Unfortunately, our silver tab shorted out due to a lack of concentration of fibers. However, this wasn't a complete failure, since we had some extra fibers from the spin left over, and all we had to do was put two pieces of aluminum, one on the top and one on the bottom, to create a piezoelectric tab. Now, our piezoelectric tab had pretty good results. We had two different types of tests, one of them being a tap test, so similar to, I guess, a raindrop, and a second test, a pressure test. Now, the first test worked out pretty well. As you can see on the top graph, we have a light tap being a smaller spike, and a larger tap later on in the graph as a bigger spike. And our second test, the tap and hold test, worked out pretty decent as well. In the beginning of the graph, as you can see, it spikes when we initially press down on it. But as the change decreases, so does the voltage. Then once we release it and it changes back to its original form, it spikes again.
So thermoelectric works by when there's a temperature difference in the air or in a small area. So this image is a perfect example of how thermoelectric works. So as you can see, heat usually gathers on the roof of the house. So the hotter area is on the top. So we want to imply the thermoelectric principle on the roof of the house. So a thermoelectric generator works by when there's a heat source and a cold source, and there's semiconductors in between those two, and it produces an electrical charge. So we want to harvest an electrical charge for a thermoelectric generator. So the first test that we did, we spun a PVP solution onto a glass slide, but it didn't work. No first experiments work. So as you can see the picture on the left, the fibers were blowing back into our syringe pump. So we had to figure out how to fix that. So what we did was we got rid of the glass slides completely, and we spun directly to aluminum foil, and we put that into a foam box with a heat source and dry ice, turned the power on, and we got a current and a voltage. So as you can see from our graphs, the graph on the left shows the temperature difference of the box with the heat source and the cold source, and that correlates with the graphs on the right. You can see that the higher the temperature difference, the higher power, amps, and voltage we get. So if we had more time, we'd like to combine all three methods into just one single battery, but end this school year. Thank you for your time. If you have any questions, we'll see you in the audience.
Imagine a world where you could walk into a room and your phone will start charging. Hello, my name is NG Koshit, this is Scott Schrum, that's Noah Went. Together we make up NASTech, and we are excited to share our wireless energy transfer research with you today.
So for everybody who's ever had an electronic device of any sort, which I'm assuming everybody in this room can safely say they've had, they all come with all sorts of wires that you have to deal with, and these wires can become a problem. They can short circuit, cause fires, you can trip over them, break them, and all of this could be avoided if we just had wireless electricity transfer. But this seems far-fetched, but it's quickly becoming a reality.
So when a lot of people first hear wireless energy transfer, they don't necessarily believe that it's a thing, but in reality, it's in a lot of today's technology. So if any of you have a Samsung phone or an Apple Watch or even an electric toothbrush, these all charge using wireless electricity transfer methods. But the thing is, they're all very close proximity, and not many companies are fully capitalizing on the capabilities of wireless energy transfer.
A company that has capitalized on this technology is Vitricity. Electricity has developed these charging pads that you are able to place either on top or below a surface, such as a kitchen countertop. As long as you place your phone within that surface area of the charging pad, it can charge. But if you accidentally knock it out of the way or you lift it up, it will stop charging. We want to take this technology and make it more mobile and viable.
So before Witricity was the company that they are today, they were a research team at MIT. And in 2007, they were able to run an experiment where they could fully illuminate a 60-watt light bulb over a distance of 2 meters while being physically disconnected from the power source. So the schematic behind me depicts that experiment that they were in, which consisted of an oscillator which sent power to a source coil, which then transferred that energy over 2 meters to a device coil, which was then picked up by the load, which in this case was the light bulb.
And in that first loop, there is a Colbit's oscillator which rapidly alternates the current, and in turn that generates a magnetic field. And we wanted that magnetic field to be as strong as possible, so we wanted the flux to be as strong as possible as well. So we coaxially aligned the 2 coils, and then when the magnetic field reached the second coil, it would turn into an electromotive force and turn into a voltage, which would then power the light bulb.
So instead of just jumping right into MIT's research, we decided to create a smaller scale version of what they had created in order to save up on all the resources that the full scale version would have, require. And what we did is we created basically what they had. We have a source coil, which consists of a resistor and a transistor and a battery. And then we also had a device coil, which was connected to an LED. And as you can see in the picture, they are physically disconnected, and at a range of about 3 centimeters, they can still light up without even touching at all.
So after making this coil system, we decided to further experiment with it. And one of the things that we tested out with was adding a third coil in between the source and device coils with the same parameters as those first 2. And as you can see in the video behind me, when we add that third coil between the first 2, we can almost double the distance that energy is transferred.
We also decided to test out with different materials. So for example, we used galvanized steel for that third coil, and we found that it completely cut off the signal. We also wanted to test out the correlation between the voltage, current, and distance of the coil system. We found that, as expected, when you increase the distance, you also lower the output current and voltage.
So one thing that we found interesting was that while the current cut off at around 5 centimeters, which was when the LED stopped lighting up, the voltage was still picking up at around 12 centimeters. And another thing that we found interesting is that the voltage actually peaked before the LED lit up, and then the voltage dropped a little bit, and that's when the current picks up at that spike right there.
So the next thing that we did is we decided to create what powers the system that the MIT group did, and that is the Colbit's oscillator. And the Colbit's oscillator is comprised of a tank circuit, which is an inductor in parallel with 2 capacitors. And this is the part that, like Angie said, rapidly alternates the current, which is able to power the system itself.
So after making a breadboard, we decided to make a printed circuit board, or PCB, to ensure better connections between the components and in turn better results.
And after we were able to get the frequencies, we wanted to test them out for consistency and accuracy. So we made 3 Colbit's oscillators and measured the frequencies 2 different ways. And between the 6 measurements, we found that there was no more than a 0.922 discrepancy between all of the measurements. So it's safe to assume that our Colbit's oscillator is fully functioning and that we are able to make a larger scale model.
So with more time and resources, one of the things that we'd like to experiment more with is the Colbit's oscillator, because while we created a Colbit's oscillator that could generate the correct frequency, it didn't have enough voltage to push a current through that first coil. So another thing that we'd like to experiment with is making a full-scale model of what MIT did with the 8-gauge wire, and another full-scale model with 12-gauge wire, which is a little bit thinner than the 8-gauge.
We would also like to try adding a third coil into our full-scale model, like in the smaller scale model we did where it increased the distance we could transfer. We'd like to see if in the full-scale model, using that third coil, we could increase that distance even further.
And finally, we want to change the load at the end of the coil system. So instead of having a light bulb, we want to try having a phone or a laptop to see that the coil system can actually be used in everyday life. Thank you for having us, and we will take questions in the aux drum.
Hi, I'm Jason Sands.
I'm Jonathan Storms.
And together we are Sandstorm Technologies. As you can see, football can be a fairly brutal sport at times. Each of those hits that you saw is probably going to end up leading to some sort of concussion or other traumatic brain injury for the players involved. But it doesn't end there. It's not just football players who can suffer these. Every day in the United States alone, over 153 people die from TBI-related injuries or concussions or anything of that sort. And over 22% of those were people ages 15 and under.
The reason why that these injuries still occur is that although helmets are designed to prevent injuries, they are only designed to prevent head-on collisions, and they are not made to prevent rotational force, which is caused by angled impacts. And the reason why they are not designed for this is because it would be too impractical to test every single possible angle that the helmet could be hit by. Now, they are made with hard polycarbonate, a second layer of flexible plastic, and then a final layer of viscoelastic material, which is used to absorb the vibrations that would mess with the brain. And the average test for a football helmet is that it is put on a dummy, and then it is dropped down from different heights to test different impacts.
The three main concepts involved in a head-on football collision are impulse, torque, and momentum. Impulse is just simply put an amount of force over a certain period of time. Torque is just the amount of force needed to cause an object to rotate about an axis, and momentum is just how massive something is multiplied by how fast it's moving. These are the three main factors that contribute to TBIs and concussions in football and other sports. Now, we've tried to correct this by making a special kind of solution called a shear thinning solution. How it works is it starts off in a solid gel-like state, and when you apply a force to it, it absorbs that force and turns into a much more liquid-like material. Now, we made ours out of deionized water, xanthan gum, and aluminum powder. Xanthan gum is a very common food additive used in everything from ketchup and ranch dressing to different kinds of pastries.
We used deionized water because it does not react with xanthan gum or the aluminum powder. And we added the aluminum powder because it increased the viscosity of the xanthan gum, and it also made it so that it was able to last longer before the xanthan gum broke down.
These are just a few images from our testing, and you can see up here, our materials that we made, and that's just our basic testing apparatus, which we'll get more into when we're down in the gym. From the results of our testing, up here you can see these are just the averages of our different tests. In the front, you see these are our readings with no padding. We have the voltage as the blue bars and conductance as the orange. Our goal was to try and get the lowest possible reading for those two. So we tested against different materials like polyurethane foam and sorbothane, which are commonly used as insulation and padding for different things. And as you can see, the sorbothane didn't perform so well, but polyurethane foam did. And although it did perform well, our solution over here on the end, you can see it performed the best out of all of them because we got the lowest numbers out of everything, so it absorbed the most force. If we had more time, we would try and test it against actual padding in football helmets, which we didn't quite have enough time to do this year, and if we were able to do that, we'd be able to synthesize a much more optimal and more stable xanthan-gum solution.
We also would have tested to see if we could potentially redesign the football helmet so that it would be easier to integrate our material into it, possibly having a shell or having veins along the inside.
Thank you for your time. We'll answer all your questions down in Jim's.
Good evening. My name is Jonathan Denny. I'm the Kendrzak, and together we make the Thermoelectric research team. So let's start with some of the basics. What is thermoelectricity? Well, in basic terms, it's energy from heat. Okay, most of us know that by now. But delving deeper into it, how we characterize it, for instance, involves the Seebeck coefficient, which I'll delve deeper into further in this presentation. But for now, it involves a rather large temperature difference involving two conducting metals.
So why do we need thermoelectricity? Well, heat is an abundant source that everyone is surrounded by right now. It's lost in the environment, no matter what we do about it. We can't get it back right now. But what if we could? What if we could get back all that lost heat from your cell phone, the lighting, and even your house?
And so, throughout this year, that's what the two of us have been doing. So, we decided to harness this energy, not via metal, but by a nanofiber. So, how we created this was through two nanofiber solutions. The first one being a nitride solution, and the second being a PVP and ethanol solution, not too unlike what powers some of the cars you drive.
After we mix those two solutions, we would then electrospin them to a sheet of aluminum foil. After that, we would then anneal them for 3 hours total. The first hour would be about 300 degrees Fahrenheit. The second hour and the final 2 hours would be for just under 900 degrees Fahrenheit. This would help remove any of the PVP that might still be around in the nanofibers.
This here is the resulting nanofiber. And to characterize the fiber's ability to create voltage, swinging back to the Seebeck coefficient, we utilized a styrofoam cooler, dry ice for the colder portion, which can reach temperatures in excess of negative 100 degrees Fahrenheit, and a power resistor, which can reach temperatures of positive 100 degrees Fahrenheit. Applied a power source and just marked every temperature for 40 minutes straight. Tedious, but the final result is up there. And as you can see, I don't know if you can see it, but in the graphic there, when the temperature difference and the actual heat temperature are higher, have extreme differences, the voltage is higher, as indicated by the green line. When they are equal to each other, the voltage, again the green line, is its lowest, further proving the result of the Seebeck coefficient. Okay, so I bet you're all wondering, how does this impact me? You know, I've spoken all about the science stuff, but how does it impact people like you and me? In the future, you could use this to power homes, cars, you could even make shirts out of it, because think, when it's cold outside, that causes the nanofiber to heat up, so you're not having to wear a big jacket all the time. And lastly, the cell phone, which is the one example that I like to use when using the nanofiber. So think of it, we're on our cell phones all day, 4 to 6 hours, social media, news, texting, etc. After a while, that phone begins to get hot, and where does that heat go? As mentioned earlier, into the atmosphere, unused energy. So what if you could harness all that energy back into the phone, thus reducing your need to charge all the time and be constantly glued to that outlet, or having your hands get hot from the phone being too hot? Just some food for thought. Okay, well thank you all for coming out this evening, and at this time, I'd like to announce
Good evening again. Thank you very much. What you just witnessed were the 9 research teams as part of our Engineering Design and Development course, as part of our Engineering Academy. I would like to introduce you to one more team that I worked with this year, actually one of many, but with one more team that we will be sharing with you tonight. That's part of our NASA, our North Penn NASA research team that started last year. We were able to do some research with hydrophobic polymer nanofibers. We were introduced by J.J. Ramond from Montgomery County Community College, if you want to stand for a second. And JJ has been working with myself, Dr. Wojciech, and several other teachers in our department to open up doors of opportunity for our students. And one of the doors of opportunity that opened up last year was to work as part of the NASA research program to actually develop and test the hydrophobicity, or the water protection of nanofibers to keep electronic circuits from breaking down in space flight or in autonomous vehicle research. And so we also were blessed with the opportunity to have a student who graduated from the Engineering Academy last year, who is now also at Monco. That's Nick Cyberlick, if you could stand up for a minute. He's done a lot working with the team that you're going to see coming out now to help bring them up to speed, because while I see my students every day for a period and a half, I only saw the NASA research team every Tuesday after school. And we didn't start our official research this year until after the new year. And so to see the work that they've done, I'm really excited to bring them up here and share with you a little bit of the work that they've done, and then they'll talk to you a little bit about what's coming up next, and I can't wait. So again, thank you for your time. We have one more team to go. Thank you.
Good evening, everyone. My name is Tyler Euler.
I'm Cameron Russell.
I'm Satyam Patel.
I'm Daniel Trump. I'm Bryce Furyk. I'm Jay Colbert, and we are the North Penn NASA research team. So we're in the second year of a 3-year program on a grant from NASA and the Pennsylvania Space Grant Consortium to attempt to research using polymer nanofiber, superhydrophobic polymer nanofibers for the protection of electronics in spaceflight and autonomous vehicles.
So we're all new to the process of polymer prep and electrospinning, so the first couple of meetings that we met together, we had to go through the process and get it down pat. And given we have 3 sophomores, 2 juniors, and Tyler over here, we had no idea what we were getting into. We had no idea what a nanofiber looked like or anything anywhere close to it. So our first spin was polyethylene oxide, or PEO, and this was our first spin, thanks to Tyler. And once we saw this, we were amazed. And this gave us basically the green light to move on with our research and to figure out our hydrophobic nanofiber.
So the problem that we were investigating is that electronics in spaceflight would become damaged by water, and that the connector for the electronics was the most difficult to protect. So our goal was to use different electrospinning techniques to coat the electronics with nanofibers, but we must first test the current water resistance of the connector. So to do so, we use a multimeter to connect to each contact point, and we would test the resistance before and after entering it into the water. If there was a difference in resistance, then we would know that water is seeping inside the connector.
After realizing that we did in fact have a problem, we went on to developing solutions. Our first idea was to put the connector in front of a grounded plate and spin to it. After doing this experiment, we realized that this was not a viable solution, as it only coated to the front of the connector and not fully around it as we were hoping. Then, after that was not what we were hoping for, we went on to developing other solutions. Our next idea was to connect the connector to a motor and have it spin as the polymer is being spun to it.
This solution was not a viable solution because the connector was very difficult to remove without disturbing the nanofibers, and doing so would create holes in the covering, which would allow water to leak through still.
We do have to give props and thanks to Anovo for letting us use their goalpost design, but sorry it didn't work out.
So we realized that both possible solutions didn't work, so we had to go back to spinning onto an aluminum foil plate and then pulling off the PLC and then wrapping it onto the connector. Once we did so, we decided to heat shrink it to see if that would have any effect on its ability to bond with the actual connector.
The first time we heat shrunk the PCL polymer, we noticed that the holes and gaps within the fibers contracted and making it more rigid and hydrophobic. Then when we tested a piece of the polymer with tweezers, we stretched it apart and noticed that the fibers wrapped around each other and was very stretchy and like rope.
The second time that we heat shrunk the PLC, we noticed that though many of the fibers had contracted and gone away completely as if they had melted, some of them remained, as evidenced by the numerous striations in the picture on your left. We interpreted from that the material would remain strong and flexible, and limited testing proved that.
The third time we applied heat to the PCL polymer sample, we observed that almost all the holes and gaps were filled and became very rigid, but still held its flexible characteristics. It also created a pitting effect.
So the current electrospinners on the market are very bulky and are limited to an enclosed location. So having a portable electrospinner would open up new applications. For example, an EMT could electrospin right to a wound at the scene of an accident, or in the case of Chengdao University, they're able to electrospin to any object, and they could create maybe a nanofiber coating that's waterproof onto any object.
Now, current bulky electrospinning devices are obviously impractical for those types of applications. However, research from outside sources suggests that it is feasible to create a portable electrospinning device with off-the-shelf hardware today. To this end, we intend to put in more work on this next year. We've already developed a schematic for the power supply, which would step 9 volts, found in a 9-volt battery, up to the high voltages at which we would electrospin at. We intend to continue development on the portable electrospinning device in the coming year. We'd like to thank you all for coming. If you have any questions, we'll be in the auxiliary gym. So thank you very much. Do you have the slide projector so we can go to the next slide, which I think is all of the teams again. Thank you very much for coming out. This is the first half of the evening to share with you all of the work that the students here at North Penn have been doing. I'm in awe every day. They inspire me so much. They just drive me, they're my motivators. So I'm really excited for them to share with you their work and can't wait to see what they do once they graduate from this institution and open up many doors of opportunity for themselves in the future. Again, thank you again to Montgomery County Community College and JJ and Nick as well, and NASA for giving these students their opportunity. At this time, I would like to call all of the EDD students up just so you can see the entire research team of researchers this year. And if anybody wants to get pictures, please feel free. This is the graduating class of the North Penn High School Engineering Academy. While they're coming up, I want to let you know too, there's a ton of opportunities at North Penn, and one of the things I didn't even mention, but I do feel like I need to, in case you haven't heard, we were invited, all of us, were invited to go to London this year to present our research and our work as part of an international science collaboration. And unfortunately, we were only allowed to take 8 students. So we were able to take 3 teams. So of the students up here, 3 of the teams were able to represent the United States at this International Science Conference. It was the first time. And all of these students, not just those 3 teams, deserve a round of applause. At this time, I would like to congratulate you seniors. Congratulations on such an awesome year. You've inspired me to be and do the best that I can for you, and I'm really excited for you, and I hope and wish the best for you guys as you go on and continue on with your endeavors.
And again, thank you all for coming out. We're going to head over to the auxiliary gym next, where we'll have the opportunity to actually take a look at some of their research in action, as well as take a look at some snacks and other things as well. And, which is always good, and a live demonstration of the Hitachi TM3030 from Angstrom Scientific, who drove all the way down here from northern Jersey tonight to actually demonstrate this for us. So you're going to see that live in action as well. So again, thank you all for coming out tonight. We'll pick up the second half. And congratulations, everyone.